bits, K user K, and this WTR describes the waveform of the monocycle, and the TK means cosine is just go from the beginning of the universe to the end of the universe. Okay, so the time just keep going, and this is the boundary TF. You have a frame boundary, and here the TC is the jumping within each frame. This monocycle can jumping at a different place. How do they jump is depends on how do you assign the pseudo random sequence. The reason is you don't want to stay always at the same place. Otherwise, once it's subjected to the interference, then all your information lost. You want to let it jumping according to the pseudo random sequence. And as I mentioned before, the nominal distance it decided whether this is 0 or 1. So you have this delta G here. And usually the number taken is the frame boundary is about 100 nanoseconds, and the hopping, the chip is 1.5. TM means this impulse is about 0.7 nanosecond. So it's very, very small. 0.7, you say 1 nanosecond gigahertz. Okay. So then the delta D, the difference between this 0 and 1 is about 0.15 nanosecond.
So where did you get this data?
Oh, this is from Marty-Wing's paper. This is
Wing's paper.
Yeah, Wing's paper. Here I just keep talking about first introduce this background, and at the receive side, as usual in the communication system, you just compute the autocorrelation. The receive information with a jitter version, and the one generates at the local regenerates, and try to see where it has a peak. Look at this delta. The delta, it looks through this NS is not just looking once, because one cannot make the decision. You look at several of it, say hundreds. Then, based on the majority of it, you say, okay, if the D is greater than 0, it's called decision statistics. If it's greater than 0, you say, oh, transmit is 0 versus it is 1. So at the receive side, you generate this sequence. Okay, generate first delta function, and you know the frame boundary, and we know what is the pseudo random sequence because you know what the user will try to receive, and the chip rate you already know. So only thing you didn't know is you try to guess where it's sitting at 0 or 1. You just try to guess it. Okay. This ultra-wideband stuff is good as long as there's no time jitter. Because you think about if there's between this 0 and 1, the distance is only 0.156 nanoseconds. So it's very close to each other. If there's a 0.1 nanosecond time jitter, this is 100 users in the cell using the UWB, and this is 200 users. Then if there's some jitter, you can see the image get distorted. Okay. So what we are working on the problem is how can we design a system which can tolerate for time jitter? I will show you even when the time jitter is getting high, you.
So what will cause the time jitter? I mean, failure in synchronization or what?
Yeah, failure of the synchronization or something, due to the environment change or something. Because you cannot really design a system assume there is a perfect, So we try to see whether there is under the. Okay. Now, basically, this research is the problem is how can we find a modulation scheme under the time jitter condition and still can work. So that's the problem. And why it's important is because UWB encounters this problem. So next is we need to find a solution. Solution is one thing is you just instead of using this monocycle with 0.7 nanoseconds, you can enlarge it a little bit so that it will not be so subjective to this time jitter. But enlarge it means this gigabit becomes the megabit, no longer destroy the original purpose. And what we are working on is using a bio-phase polarity, using like a solid 1 is 0 and dash 1 is for 1. So because this transmission is better in terms of time jitter, anti-time jitter is better, instead of based on the position, based on their polarity to make the decision. Then you need to do this decision statistics a little bit different. You have the waveform, monocycle, WTR, and you have the frame boundary, pseudo random, but when you make the decision, it's no longer this delta ET, and all the decision actually is making and this phase stuff shift to here. That's what's the bio phase. So the challenge actually lays in how to design such a waveform. You want to have the orthogonality to each other. so that you can detect which one is 0 and 1, right? Try to make this orthogonality under even the jitter condition. This is a very mathematics problem, okay? So what we check under the same bandwidth, okay, that's become a very mathematics. I think I'm not smart enough to work out the analytic solution. We work out a numerical solution. We propose is called, the waveform is high orders monocycle. High order because this n can take the order a little higher than only 0 and 2. And the integration for this transformed information should be always the average should always be 0, because we know the antenna transmission, you need to make sure the DC is always 0. So the waveform, what we propose, the waveform looks like this. Here we're choosing the n is equal to 15. Okay, if n is equal to 1, then it just boils down to this Rayleigh. Rayleigh is the odd symmetrical waveform. People using this Rayleigh monocycle to transmit information. If this n is equal, then this is just to boil down to the multi-rings or the monocycle, second order statistics, or the derivative of the Gaussian. So this is the monocycle. Usually we call this is, one of my students calls the Mexican hat. Mexican hat, okay? Looks like a Mexican hat. And so, now let's analyze. If we transmit the information, we need to look at what is the decision statistics for our proposed scheme. So basically we need to do the same thing, okay, to look at what's the autocorrelation between the received signal. Just take a Rayleigh here. For example, come out a pretty messy equation. Yeah, it's good for this paper. Now, if you plot out this Rayleigh, you can see this solid one, say it's 0, and this dot is for 1. And overall, you have this up and down because the DC value need to be 0, right? So you have to have some up and down. Overall, the average of the spectrum should be equal to 0 or anything. The problem is, as long as you have all the information stay in this, we call the correct decision decision duration, CDD region, things is fine. But once you go out from here, oops, you will get to the wrong information because 0 can be 1, 1 can be 0. Okay, that's it. So we put side by side. What we propose here is, okay, you want to have this CDD region as much as bigger as possible, right? So we just do the n equal to 15 for our proposed scheme. Our CDD actually is 0.4. This it's the same bandwidth. We're not doing any cheating things. Okay, we compare orange by orange and apple by apple. Okay, so this CDD is about 0.2. This CDD is about 0.4. And one more thing is, this is once it goes through the CDD region, sorry, it's on your own. But for us, we have this called TP. It's called transition period. Instead of making the wrong decision, we have a transition period, neutral. I do not make yes or no. I just let it stay for a while. So better than just making the wrong decision. Then you after this one, which means if the time jitter too big, I give up. Okay. Now, why I'm choosing 15? Go ahead.
In the previous slide, are we assuming that in the CDD an error cannot occur wherein you get the, like you told when you go outside the CDD you have a possibility of mixing a 0 and 1, right?
Definitely.
Can't that occur within your CDD?
No, will not. Because why you think this CDD is out is within this region, right? You can detect the correct information. Out of this region, in our case we will, but our region is here. We're pushing a little bit far. So overall, this is what the jitter actually can tolerate. For us, is we try to make a jitter a little, more tolerant. For them, this is like once you go out this region, good luck. You definitely will get the flip. I will show you the simulation result. And why we're choosing the n equal to 15 is because we plot this different order of this monocycle. And to look at the CDD, actually CDD is not going to forever, we hope. But this is more like a MOSFET. Go for certain, then peak out. Then the transition period can keep going on. But when you do more high order, hardware cost also is going high. So we want to choosing something in between. We're choosing 15 here. Now, how do we design such a waveform? Okay, design waveform for this one. We can do a little mathematics. Is say if you take a 0 order, then this is just e to the minus t squared. Not consider about this constant stuff. first order is this one, second order is this one, and so on. So what you want the waveform is Tn, something like a high order with like I want to have this one. Then some of this stuff can cancel out. If you have times 6 of this one plus this one can cancel out, which means even using the linear combination of this original monocycle or Gaussian form, okay, just Gaussian form, the current monocycle is second order derivative. Ours is, do several derivative like a cap, like a design the future. You have certain coefficients, then we can generate this high order statistics. Now compare the simulation. And first simulation is we say, okay, let the jitter keep going from no jitter to 0.3. Compare our performance with the different design. So we compare with the mono cycle and the Rayleigh, using the Rayleigh and look at ours. This is the performance. Picture means 1,000 words. If you have this 0.2, before I'm using the time jitter is only 0.1, now using 0.2. This is unbearable. You cannot tell the image anymore. But in our case, yeah, things is getting worse, but it's not as worse as this one because we have the protection region. If you say, okay, keep going on, yeah, our stuff also will blow out. Okay. So also we talk about if there's multiple user going on to this one, what happens? Okay, say if you have multiple user and every 100 you make the decision, and the user from 50 to 500 users, then we compare ours is here, the design over there. Okay, overall seems like our system is better, and also we changing both user and the the decision making things, changing both, and overall is still better. Okay, design this waveform. People say, how about make the FCC compliant? Because FCC has the other thing is say, okay, you cannot transform information from 0 Hertz to gigahertz. It's like you cannot demolish the other person's house and you say, hey, excuse me, I want to build a house, unless you're very powerful people. And so in the low bandwidth already have the GPS and the narrow band, the UPN, this already existing stuff, PCS stuff. Need to protect. And the other is 802.11a is here. It's around 6 gigahertz. Okay. So only allows transmissions in this region. This is FCC mask. Now it's getting difficult because if you impose some more constraint, problem is getting more and more difficult. Now we talk about this BPM. Who is working in this area? Whenever you do this one, your advisor always asks you to do the survey and to see what's the roadmap. So there's people, Harris, Chen's, we say ours is called Chen's. Okay. Now let's look at each of the designs. Harris design says, okay, this I cannot go. This is IEEE 802.11 and transmission information here. How do they do this one is, okay, you can transmit all the information. Now I design a band limited filter. Okay, only let the information at the lower stop band and high stop band only allow the information going to there. So if you have this frequency domain, you allow this FL say 6 gigahertz to 10 gigahertz. Then in the time domain you just do the opposite, numerical opposite. Then design this waveform. Okay. So basically you need to solving this matrix. This is a waveform eigenvalue. This T is your eigenvector corresponding to your waveform. And with this impulse response confined in certain region, and you still want to preserve the original kind of property of the information. Integration is difficult. It's like an analog. We go to the discrete summation, and n is sampling rate from minus n divided by 2 to n2. So overall, you need to solve this matrix. Lambda is the eigenvalue. Then you need to determine what's the eigenvector corresponding to it. And this is just the matrix we're talking about in the previous. Now, if you look at the time domain, this monocycle looks like this. This is where you're choosing lambda to be one set of the eigenvalue, and this is another set of eigenvalue. Look at corresponding spectrum. Pretty good. Fit into the FCC compliant. The problem is, this have the same problem with previous I talking about is as long as they are orthogonal to each other, or there's no time jitter, this stuff works good. When there's a time jitter, and also it didn't avoid the 802.11 because 802.11 is something here. didn't, should have a dip, a valley here, no valley. Another is Shen's approach. A Shen's approach is say, this is a Gaussian monocycle waveform. Just keep doing the derivative. 1, 2, 3, 4. This is their paper. And in doing it, you find all the frequencies just keep shifting to the upside. And this is the waveform in the time domain. It's the same problem. If you have n equal to 10 and n equal to 5, keep shifting. But the same problem as the previous Paris design. You need to orthogonal and also cannot avoid 802.11. Look at ours.
Have you ever seen the ether wire pulse?
What do you mean ether wire pulse?
You know the company ether is it ether wire? Ether wire. AETHERWIRE. They're out of California. They make like one of the oldest companies in Ultrawideband. Their pulse looks a lot like yours.
Oh really?
Yeah.
Oh.
But I'm sure they didn't do the analysis. They just found something useful by by experimentation.
Oh really?
Yeah. They have a website, etherwire.com.
Okay, maybe you can forward to me and I can look at it.
Yeah, just that's
Apparently I didn't know this.
No, I mean, like, I don't know if they do the analysis for jitter, but they have a pulse that looks like this.
Okay. So, sorry. This is the proposed high order, but in order to make the FCC compliant, we need to do some modification here. This is after modified and make the FCC compliant. We look at the spectrum of our one. The one is look like this. This is 802.11. Lower band. Ours had problem because it didn't fill up the whole band. So what we try to looking at is one of the reviewers said, you need to fill up this band. We need to try to mirror the mapping, the flip one, and we're working on this one. But this is at least is our try. Looking at the different simulation with this FCC compliant one, 5 orders and so on, do the same simulation results. Ours is still better. So we can work on this kind of numerical results which can counter for the time jitter, meanwhile can satisfy FCC mask. So for the first portion of the talk, I conclude here is propose a waveform modulation scheme for the time jitter robustness UWB design and expand it for the FCC and IEEE 802.11 transmission. And the waveform can be generated by just linear combination of the derivative, and we achieve the same bandwidth as what the original one.
So can I ask you a question?
Sure.
Like,
don't too hard.
No, it's more like something that I have no clue. Like, you said you can do these derivatives and you showed us the circuit. How, is that doable? How efficient is that circuit? How much loss do you have? Is that a very easy circuit to make?
Yeah, the derivative one, same thing for the current monocycle one. Is the second order derivative of.
Is that like an RC circuit?
Yes.
Based in RC?
Yes.
And do you have loss, or does it matter? It doesn't matter. Right?
No, this is just a tap filter. You just do the derivative of the original one, just like a monocycle one. You have the input, you derive this. There is a certain, using the MATLAB. The MATLAB can generate. This actually is the ultimate.
I just mean physical hardware implementation, not mobile implementation.
No. The differential circuit.
Right.
Just to the derivative. Derivative, you have the capacitance, and you have open. You're using open as the
IC circuit.
Yeah, IC circuit. I'm the IC guy, so I think that's the reason when I students propose this one, I say better talk about how to design it. Otherwise, people will.
Have you built? Is it easy to build? Like op-amps at this gigahertz range?
Sure, if I get money.
But the difficult part is the coefficient.
Coefficient is not difficult.
Because the dynamic range is so high that you cannot adjust. If the coefficient is not adjusted properly, you cannot get all sorts of dynamics.
Oh, sure. You need to design this one.
In reality, I don't think you can realize the order like 7 or 15. If you think about the first pulse, the difference between the amplitude of the first pulse and 7th order pulse will be like 1,000, even more than that. So how do you realize an amplifier or something like that? You can accurately realize the dynamic range from like 0 to 10 to the 4th of order. That is mathematically, or in MATLAB is realistic, but in reality, I don't think you can realize that.
Okay, do you want to be my student?
Oh, Well, actually, Professor Vasily and
tell us where to get the money to make it.
I think there's another issue. If you do consecutive derivatives, it amplifies noise tremendously.
Sure. We actually, in the nano circuit design, we talk about how to deal with the noise. We haven't go into this real, diving into it. I think when you do the AC design, there is something we'll be, need to carefully looking at it.
So if I understand correctly what we have seen, so you're taking this image, which is MATLAB matrix, and you're putting it into the simulation model. Okay.
Yeah, so far we did definitely in the circuit design of all of your comments.
Since you were talking nanotechnology, I thought you were implementing this as well.
Yeah. So actually we have some circuits can deal with the noisy, because in the nanotechnology, circuits go into the low power, and we try to develop some kind of circuit which can counter for this noisy environment condition. But definitely, I think it's very interesting to implement it.
Do you know anyone who does it, implementation?
I think the time domain there.
Well, yeah, in the companies, right? But is there anybody in the academia who has the money?
Not this, the NSF is like, if you log on their website, unfortunately they just say like digital design stuff is not really interesting in 2003. So for us, it's like this whole wireless or information technology thing is just big. Last year I talked to people, there's a wireless couple proposal, there's 128 submissions and only the funding 4. It's like funding rate is but anyway, I think this is simulation. I think in the real design, definitely what you say, this dynamic range and so on, need to go into more detail and looking at it. Definitely. Now this is just 204's publication recently. We are also working on the physical layer on different systems. Also for this synchronization problem in terms of the time jitter in this, when you transmit the OFDM signal, how under the multipass fading, and how can you blindly synchronize with the transmit with synchronization, and design algorithm can be efficient. So we have 2 papers actually accepted. One is in the actual transactional signal processing, and the next talk I'm going to talk about a little about network design. I think I'm more trained to be a physical layer design, and now I also try to see how to moving the design using the networking on top of it. So let's march on for the second portion. It's a cross-layer QoS content delivery. Again, the motivation why I'm doing this research. The significant difficulty in developing the IP network. Nowadays, everyone is talking about using IP. When I was in Muslim, people talking about ATM versus IP, people is fighting, like Democrats versus the Republican, who wins. Now it's very, very clear who wins. IP network wins. And the problem is how to meet the QoS requirements, because the link is very dynamic. When you transmit through the channel, you have multipass, you have different dynamic link characteristics, and also resource contention. You have not only one user, there's many different users competing for the usage of the resource. So the conventional protocol structure is inflexible. Basically, physical layer just work in a physical layer. You can look at the CDMA 2000. I used to work in the standard body for this CDMA 2000, and all people from Lucent, Qualcomm, all is talking about engineering technology kind of approach. But later on, you can see the IEEE 802.11. It's from the computer science approach, more like a data network. And now these 2 things need to merge together. If we say we can try to break down the wall between engineer and biologist, we need to at least bring down the wall about networking and this physical layer. So in such a design, the layer is designed in the worst case. Like the physical layer, always design is how to design the best reliable system without really knows what's application or what's current channel condition. So have to do the adaptation. Adaptation means it's a centerpiece of the cross-layer design. Is how do you can adapt to the network and based on the observed, then response to this one. So more like based on the different users' demand, based on the current channel condition, how to dynamically adjust to the need and better use of the bandwidth. Overall, is try to get limited bandwidth, how to satisfy the most of the user's need. This is a sort of another mathematics problem. So there's many proposed schemes like power control, rate adaptive, and the dynamic channel allocation, beamforming, multi-user detection, joint design between the power and beamforming, and the rate control, and so on. So in general, this cross-layer need to involve very different layers. You need to go through, in our design, we try to involve the application layer, we need to involve TCP layer, and need to involve this net layer and physical layer. So 3 or 4 layers need to talk to each other. So the adaptation can be taken in the underneath layer. But why we are interested in the TCP IP is because all these applications built on top of it doesn't need to be changed because it's kind of transparent or insensitive or indifferent with the underneath physical layer design. So that's what we try to build our protocol on the TCP IP network. So several challenges or several things can do. At the application layer, you can adjust the media source rate. You can adjust different encoding rates and so on and so forth. And the transport layer, you need to adjust the package, various package size. How do you transmit information? In the TCP, for the data network, you transmit information. If the receive side didn't receive it, then you just need to retransmit. So you need to think about how is it better to design this one. So this is more like circuit switch versus a packet switch IP network. So, okay. And in the link layer and the network layer, the link layer should schedule based on the application layer to schedule the user a little smartly based on the current condition. And also, the best is try to predict. If you can predict what's the network behavior, that will be better. If someone can write a code to predict what's the future stock, tomorrow's stock, then that's good. So this is what's wireless line data IP network moved to the mobile network, just like what's used to do the wireless voice move on to the mobile voice. In this, I based on this system on the frequency hopping OFDM as the physical layer design for this system. Okay, the frequency hopping OFDM, we know the OFDM is orthogonal to each other, but this is only true for the in cell, right? Within the cell. When you have an intra-cell, this kind of orthogonality doesn't really guarantee. So what we need to do is we're using kind of sort of CDMA-based approach is frequency hopping approach. So if you have cell site 1 and versus cell site 2, you divide each time into a different symbol, and this tone is to be your total carrier bandwidth divided into sub-carrier. And then you have 1, 2, this next time jumping to here and jumping to here, and the second user just jumping, and hopefully these 2 users at a different cell sites will not jump into each other. That's the main purpose, to make it frequency hopping. So in the OFDM, you try to make sure no interference within the cell. That's OFDM sort of guarantee. And also try to make sure you can average out the interference across the different cells. Now, the scheme, what we propose is to do using the residual number system for the frequency hopping. Because how do you assign? This time you have the data pattern jumping here, next time jumping here. You need to have some kind of rule to jumping it instead of using the ad hoc fashion. And you need to design this one to meet the different requirements. First requirement is to avoid ambiguity when identify user. You don't want to design the code, then later on the receive side gets confused by itself. Who is who?
Can you use a pseudo-random sequence?
No, this is not. Because pseudo-random sequence is some people already used. So you want to do something. Pseudo-random sequence is not really guarantee all this kind of property. You can use in the pseudo-random sequence. You can use in the sequence. But on the other hand, whenever you propose something, you also want to propose a better system. Like in the INS system, this is mathematics paper. People prove this based on the residual number system. You can, if you assign it correct, you can make this 4 requirements satisfied. One is to avoid the ambiguity to identify different users. Second, reduce the chance of collision between 2 frequency hopping. You don't want to have 2 hopping. The watch code, for instance, is pseudo-random code, but how do you assign it? You want to get the least chance to let the one cell site assign the same number for the different cell sites as a different. You try to make it as far as possible. Just like if you're driving a car, you try not to collide with your user and also not collide with your front user. So how do you? Watch code is just like a code, but in time fashion, how do you design this one? Next time I jump into the different code, and next time, and watch code only has say limited. How do you sort of you need to have a time fashion. Next time I jump into the different watch code, then I jump into the another one. Okay, for instance, like this. So that's what, and also try to keep the adjacent frequency hopping pattern far from each other. Okay, not step toe on the other. So what we propose is a two-stage frequency hopping mapping, RNS or residual number system. You can think about the whole bandwidth divided into the m sub pieces. And you can think about this is just like when you represent a floating number. You have the integer portion and the decimal portion. The integer portion says like if you talk about 101 mega, then this is in the within this sub-region, the decimal portion of it, like 0.05 megahertz. Okay, so using the two-stage mapping system. So in the cell site 1, this is how it works. You have user 1 and user 2, say for 2 users. And each cell site has a base number we call accumulator number. Say m is 12, n is 13. Starts from each base station has a different number. Then each user has a different ID. You want to assign each user a unique ID, say 1521. Okay, say pick up example. Then because this m is 12, so 1512, the residual number is 3, right? And 1513, the residual number is 2, right? So you have these two numbers, 3 and 2. Then this 2 number and need to add to the base. Base is 10. So this 10, 3, 13, 2, 10, 12. Then go back to the modulation. This is 13 modulated with 12. Remainder is 1. And this 13 with this 2 and 10 adding together is 12. Modulated with 13 remain 12. So this is different than. So now follow this sequence. It just keep jumping and satisfies the previous one. So it kind of lets you jumping the pattern along the time. Just follow this one instead of using the watch, because watch code you next time jumping to what? Next time, and also there's a limited watch code you can really jump into. This is like if you have a number really big, you can accommodate a lot of different users. This is a different cell site. You can have a different base number. Same kind of algorithm, and based on this RNS, it says sort of can minimize. Surely when the user is getting bigger, the chance maybe can step onto it. Now, look at the downlink design. Downlink design, we're using the shear pilot. You have a pilot which tells the channel estimation for coherent modulation. Downlink using the coherent modulation, and also tells the synchronization information, base station identification. You can, based on different pilots, you can know which the base station is corresponding to. And this red one is the pilot symbol. And the blue one is a symbol for mobile user number 1, and the yellow one is for mobile user number 2. So this is just, since it's keeping jumping around. Okay, but each jumping around is follow this RNS rule. Then for the downlink, we do the power control as well as timing control. So each of the symbol can be jumping to the next one. Hopping sequence are different from the neighbor cell. Okay, that's what we try to guarantee. And tone just hopping from each symbol and each time jumping to the next one. For the uplink, it is different because in the uplink you have no pilot. It's too cost to have a pilot. So no shear pilot, and also not hopping every symbol. Instead of hopping through a duration, we call it quiet time. So you have n number, just after the n number it jumps. N number it jumps. So you have a blue and the yellow, two different users you can jump. And using the power control. The time control is trying to make sure base station and the mobile is actually logging to each other. Sequentially, we do every second to 4 times this time loop control check. to make sure this is actually synchronized or locked to the base station. Okay, so no pilot. And how do you do the demodulation? Is using the middle of the symbol to do the differential modulation so that you can demod what's the information you transmit. And also, this is physical layer design. We need to build in the QoS into it, in the physical layer. For the downlink, all the transmission is scheduled. Uplink also, For the downlink, because downlink is base station has a lot of resource, and we're just using one option. N slot or N symbol transmits using M tone or M subcarrier. For the uplink, we support, say, different option. First option is using the time is only limited time by using all the bandwidth. What this case is when the user is very close to your the tower, and the signal to noise ratio is very good or signal is very strong, then you can using all the bandwidth to transmit the information to that user. Versus the user is far away from the cell site. In that case, signal is very bad. There's no meaning to assign all the bandwidth to that user. It's waste. So assign the limited tone, but very long time. The purpose is trying to make sure the link still hanging on. It's like a monkey bar. You want to hang on this one without dropping, because when drop, then reset, it takes a lot of time. When the channel condition is getting better, then you're using a different option. That's what we say, kind of building this MAC scheduler into the physical layer by taking the different consideration. So it's a little flexibility in the design. Now look at the TCP loopback. This is runtime. Whenever the TCP transmits the information, you need to ask to retransmit if the signal gets lost. So how do you retransmit is just keep sending it using the ACK and ACK or piggyback sort of things. So because our design is, you can go to each of the symbol and using one of the tone to send, then we can send those acknowledged information, yes or no. Basically, you want to know whether this package has received or not received. Using a very short burst, we call fast ARQ channel, control channel, to send this yes or no. So based on this fast ARQ, we can quickly turn around. So this is the simulation result. Runtime of it is about 200 milliseconds. And versus the conventional TCP, ours is better because when we send the ARQ, is using very small short period to retransmit. So the time-wise is better, just looping time or long delay. Now, this is sort of in the physical layer, building certain MAC to support such a scheme. The other is the QoS in the MAC layer has different states. We have high QoS state, medium QoS state, and low QoS state. High QoS state stands for when the people is ready to transmit and he has the token to transmit, then assign all the traffic channel to that user. Versus the medium QoS is if this user do not have the token, in terms do not have enough privilege or didn't pay enough high monthly subscription fee, then maybe kick off, or maybe this is one user using the running the voice and the other is using the FTP. You can temporarily putting this one aside. The low QoS is like if the session is not activity for a while, then you kind of put it instead of letting it waste all this resource. So look at this QoS. High QoS only can accommodate very limited amount of number of users, and all the users have the traffic and ready to send the information. For the media, you can allow a little more, maybe 128, for example. Then these users, if they're willing to, once the high user finish, it can quickly retransmit and regain without competition. Can regain and retransmit and grab the traffic channel. And low power, low QoS users, you have 1,000 users, and basically these users need to go through the contention and go back. And wake up using like paging. If you have session quiet for a while, then using the paging to wake up. So here is how the channel assignment or the resource assignment. High QoS, you have traffic channel, all things like a very privileged. You have all things assigned. The media, only have certain, and the low QoS only have the page channel is on. Now, how do you, based on what criteria you assign this different QoS state? There's two criteria. One is called QoS class. Class is like just like in Olympics. You have gold, silver, and bronze. Maybe you have iron and mud, something like that. Okay, you just assign different users based on how much monthly fee they pay, or they are good users. Okay, and the other is you need to look at what's the traffic. Even two users have the same priority. You need to look at different user class. Okay, or the stream. For instance, like a 911 call. It's high stream. High enough is you need to kick out maybe everyone and just serving this 911. And layer 2, layer 1 control. This control signal is very like egg and egg. This also is very important. You don't want to mess up around with it. Then the voice, because it has the real-time requirements. And versus FTP, you can delay it a little bit. The other is like a QAM. QAM means like a maintenance. How good, how healthy is the system, and so on and so forth. So there's a matrix. You can design this one corresponding to each stream. Bit error rate, segment loss, segment order, and delay. For 911, you want to make sure this is like a score. Strongly, don't mess around with it. It's say score 4. And okay, you can not so strong. You can give assignment is say 2, for instance. So for instance, you pick up a voice. The segment order is important, and the delay is important. In terms of bit error rate, you can tolerate certain tolerance. So it gives the matrix. Overall, you will give each one just like in the midterm, you give certain score, then you average all this one and give the final score. So how you can calculate is based on how difficult to how much cost to send each packet. Then how can you calculate the cost is based on the weight. The weight is just like in the previous one. You have different weight corresponding to this one. This is user can assign, system assign. Then it depends on how much you want this one piece. Overall, you will have an average score. And based on this average score, you can say how this particular packet, how important is this particular packet. If I'm allowed to send, then I'm doing the queue and which one should go first. So you have a QoS monitor what's the current channel bit error rate. So you need to know whether this bit error rate and channel throughput and the network loss or disorder stuff. Then this is monitor and this is wish list. You say I wish for this transmission, but overall may not satisfy you. So overall you have a kind of cost of most likely. This is my desired. This is my estimate. The overall goal is the Mac need to schedule this one, match the desired or wish list. Okay. Now let's look at the simulation. The simulation actually is work with the Flareon network and do the driving tests for this system. Go through the 6 different cell sites, and the system can have 1.25 megahertz bandwidth, and the subcarrier say tone have 113. You have can chop it into 113. Then you have such a system. You have different location A, B, C, D. So have 4 different users at different sites. One is close to the base station, have high SNR. The other is a little far away, has lower SNR, and also have different stream. One is FTP, the other is download, the other is media player, play some media like music, MPEG, MP3, and the other is web page, you're surfing the web and so on. So first, let's look at the baseline test. At the location A, the user just do the FTP, and the bandwidth say is 2.5. The system can peak. Okay. And the other is people listen to 2 pieces of song. So song after finished, second song goes, listen to the song. This is a user just downloads the web. You can see this is a spark is when there's a downloading, and this silence means the page download to you and you looking at this. Now, this is like a standstill calibration test. Next is all the car is moving around. Say this file transfer from FTP download from location B to C, and this web surfing is from C to D, okay, and this is from D to A, Okay, time is moving, and meanwhile doing 4 different type of service. This is Go user. Here I didn't assign all different user with different QoS. Say this is a Go user, good user, and first he welcomes to the system. All the 2.5 just assigned to this guy. Next user has a stream MP3 player, and this is only using 140K, so not much sacrifice, no resource competition, so both happily and running. Now, a third user is on and need to require the bandwidth about 1.2 mega. Now, both user is the same with the same previous one is Go user. They are at the same QoS class, and both is download. Okay, in this case, evenly distributed. So the first users from 2.5 drop half. Okay, we share the bandwidth half. Until the second user finished, you can have all this one until you finish. Okay, so in this case, you just share the bandwidth between these two. Now, if we assigned the first user to be a bronze user and the third one coming in, what happens is this user just boom, come down to the no bandwidth assigned, and the other user just grab all this bandwidth and take all this information. Meanwhile, the stream video, just our streaming MP3 is just playing and so on. Again, this test doesn't mean to be complete, okay, but at least just to show, how this cross-layer management for this different QoS. So propose a cross-layer design scheme, especially this among application. You need to know what's the application based on stream and the QoS class, and design the MAC and layer. They can cross-talk MAC scheduler and MAC state for the QoS delivery. Okay, it's not equal. Depends on different users' cost of each stream, and depends on how many users, and propose a QoS aware scheduler and power adaptation. Like the Uplink, we have a different option. It's not like schedule using the same option. When the user is far away, using the less resource, but give it long time. Hopefully it will come up sometime. And also the downlink coordinates the behavior of the load. Base station makes the decision finally. Mobile can request, but base station makes the final call. And our open to end-to-end IP network structure allows the inter-network with heterogeneous, because the whole network is based on the IP network. And acknowledge is for students and Microsoft Research Fairground Technology. This is my website. Thank you very much.